Welcome back to The Explainer. Today we're going to tackle something that sounds almost impossible. We're going to show you how the secrets of the ancient pyramids are being used to solve a massive flaw in one of our most futuristic construction technologies.
Okay, so let's just dive right into that. How can an ancient civilization, thousands of years old, hold the key to perfecting a cutting-edge digital technology? Well, it sounds like science fiction, I know, but the logic here is actually surprisingly direct. It connects the oldest form of precision engineering with the absolute newest.
You see, 3D concrete printing holds this incredible promise. We can build these architectural marvels, these complex organic shapes, at speeds that were once unimaginable. But there's a catch. There's a fundamental problem hiding in the process itself. The very thing that gives the technology its power, building layer by layer, also creates its single greatest weakness. And that weakness has a name, anisotropy. Now, just think of it like a simple stack of paper. It's super strong if you press down on the top of the stack, right? But it separates incredibly easily if you just try to pull the pages apart. Well, in 3D printing, those weak planes between the layers are called cold joints, and they are the Achilles heel of the entire structure. And this shows you the real-world impact. So if you apply force parallel to the printed lines, the concrete holds on to about 85% of its potential strength. Not bad. But, and this is the key, when you apply that same force perpendicularly, trying to basically peel those layers apart, the strength just plummets to 71%. That's a nearly 30% loss of integrity, all based on which direction the force is coming from.
So, to solve this very modern problem, this delamination, engineers started looking way back, thousands of years into the past. They realized the answer wasn't in new chemical binders or stronger concrete formulas. No, the answer was with the master builders of the Old Kingdom of Egypt. You have to understand, the Egyptians didn't just stack a bunch of rocks. They used this incredibly sophisticated and repeatable system where multi-ton blocks fit together with tolerances that we would struggle with today. And for them, this precision wasn't just for looks. It was an absolute structural necessity.
And here's a glimpse of how they did it. I mean, their system covered everything, from shaping these massive stones with things like abrasive sands to using simple knotted ropes to check for perfect right angles. They even used these genius things called sand jacks to lower blocks into place with pinpoint accuracy, making sure every single piece fit perfectly.
Now this brings us to the crucial concept, compression locking. By shaping the blocks with these subtly inclined or even convex faces, the sheer weight of the structure itself forces them all together, basically turning thousands of individual stones into one single monolithic object. The geometry itself was creating the structural integrity.
And this whole engineering marvel wasn't just guesswork or trial and error. Nope. It was all guided by a surprisingly simple but incredibly powerful mathematical principle that controlled the slope and angle of every single surface.
It was called the second. And it wasn't measured in degrees like we do today. It was a practical, hands-on ratio. It basically said, for every 1 cubit of height you go up, how many palms do you go across? That simple system meant any builder on a massive project could replicate the exact same slope with perfect consistency every single time.
And this diagram just illustrates it brilliantly. The C translates directly into a specific geometric angle. It's a system where the structural logic, the best possible slope for stability, is literally baked right into the math itself.
And when we translate these ancient ratios into our modern terms, you can really see just how deliberate they were. A second of 5.25 palms, that gives you an angle from the famous 3-4-5 triangle, which is known for being super stable. The 5.5 second they used in the Great Pyramid, that creates an angle with absolutely optimal structural properties. These were not random numbers. They were engineered for permanence.
Okay, so how in the world do we apply this ancient knowledge to a modern industrial robot? Well, we reverse engineer the principles of compression and interlocking, and we translate them into code.
So instead of printing flat horizontal layers that just kind of sit on top of each other, these new algorithms tell the printer to create surfaces that actually physically interlock. The print nozzle follows these really complex, non-planar paths to build corrugated surfaces almost exactly like Egyptian masonry. This whole technique is about creating what they call tooth-like interfaces, and it directly attacks that weak layer problem we talked about. These tiny, algorithmically generated teeth, they act like mechanical anchors. Now the layers can't just slide or peel apart. They are physically locked together. And the results? Well, they're staggering. This simple geometric change, inspired by these ancient principles, can increase the tensile bond strength between layers by nearly 300%. We're not just improving the bond here. We're fundamentally changing its nature from a weak chemical glue to a powerful mechanical lock.
But here's the thing. This approach does way more than just add strength. By solving the core weakness of 3D printing, it unlocks a whole new level of efficiency. It completely changes our relationship with construction materials.
So, by combining these interlocking principles with a design process called topology optimization, we can create truly revolutionary structures. The software basically analyzes where all the stresses are going to be, and it places material only along those load paths, carving out everything else that's not needed.
What you get are these incredibly strong yet lightweight skeletal forms that look more like bone than a traditional wall. And because the printed structure is now strong enough to stand on its own, this could lead to a potential material reduction of up to 72%. That drastically cuts both the cost and the carbon footprint of construction.
And this isn't science fiction. It's not some far-off dream. There is a clear roadmap to make these anciently inspired techniques a reality. Through simulation, calibrating the printers we already have, and integrating it all into building codes, the goal is to see this become a mainstream construction practice by 2028.
So ultimately, by looking to the past, we're not just building stronger, more efficient structures. We're rethinking what it means to build for permanence. By combining the oldest wisdom with the newest technology, we might just learn how to build a future that is truly designed to last.